In this video, we are going to discuss rate laws and how they are used to determine the rate of a reaction. First of all, there are two general types of rate laws. There's what's called the rate law or the differential rate law, and that shows how the rate of a reaction depends on the concentrations of the reactants. And later on, we'll discuss a second type of rate law called an integrated rate law, which shows how the concentration change in a reaction depends on time. So in this video, let's discuss what's called the general rate law. And as we mentioned, it shows how the rate of a reaction depends on the concentration of reactants. So take a look at this general chemical reaction here, where the reactants are A and B, and they react to form some products. The rate of this reaction is proportional to the concentration of A, reactant A, raised to some power, and we'll discuss that a little later, times the concentration of reactant B, raised to some power. And what you should appreciate is that as the concentration of A or B is increased, the rate of the reaction should increase as well. And we know that because collision theory tells us the higher the concentration, the more likely there is to be a productive collision and therefore a reaction. Now we can change this proportionality to make it equal by adding a proportionality constant, K, called the rate constant. So the rate of a reaction is equal to the rate constant for that reaction times the concentration of reactant A raised to some power times the concentration of reactant B raised to some power. And it should be noted that K is a constant for a particular reaction at a given temperature. So if you change the chemical reaction, you have to have a new rate constant, or if you change the temperature of a given reaction, then your rate constant will change as well. Now these exponents here, these powers, M and N, are what are called the orders of each reactant. So A has a particular exponent or order, and B has a particular exponent or order. And these indicate how the reaction rate depends on the concentration of each particular reactant. Now we're going to discuss that in more detail. And so to illustrate that, let me give you a couple of sample rate laws and try to explain what these orders of the reactions are. So let's take a look at this chemical reaction where we have HCO2H reacting with bromine to form 2 moles of H+, 2 moles of Br-, and 1 mole of carbon dioxide. The rate law for this reaction is the rate is equal to our rate constant K times the concentration of one reactant to some power, in this case second power, times the concentration of our other reactant times some power, in this case a first order or first power. Now the rate law is always going to be the rate is equal to the rate constant times the concentration of reactants raised to some power. We don't have to worry about the products when we're writing our rate law, just the reactants. So for this reaction, since the exponent for this reactant is 2, we would say it's second order with respect to HCOOH. And since this exponent is a 1, we would say it's first order with respect to Br2. Overall, the reaction we would say is third order. So the overall reaction is third order, and we get that by adding these exponents. 2 plus 1 gives us 3. Now you may be asking, well, where do these exponents come from? Well, we'll show you that in just a minute, how we determine these, but it's very important to appreciate that the value of these exponents or the orders, it must be determined experimentally. You cannot determine what the orders of the reaction are just by looking at the balanced chemical equation. You can see that the stoichiometry we have 1 mole of this reactant plus 1 mole of this reactant. Here we have a 2 and a 1. So the orders are not related to the stoichiometry. So you can never tell what the orders of a reaction are just by looking at the overall chemical equation. We have to determine those experimentally. So in this example, the orders are given to you. So as we mentioned previously, the orders or exponents show how the rate depends on the concentration of each reactant. So let me try to elaborate on that a little bit. Let's take a look at our first reactant, HCOOH, and we said it's second order with respect to this reactant. So what that tells us is if we have a certain concentration of this reactant and we increase it, say we double the concentration of this reactant, if we double this concentration, since it's second order, 2 to the second power would be 4. So what that tells us is that if we double the concentration of this reactant, the rate of the reaction would quadruple or increase by a factor of 4. If you triple this concentration from some initial concentration, if you triple it, 3 to the second power would be 9. So if you hold this the concentration of this reactant constant and you triple this one, the rate of the reaction would increase by a factor of 9. So that gives you some idea how the rate changes when we change the concentration of this reactant. Now the bromine, we said, is first order with respect to bromine because there's a assumed 1 exponent here. So that tells us if we double the concentration of bromine while holding the concentration of the other reactant constant, and we double the concentration of bromine, 2 to the first power would give us 2. So that tells us if we double the concentration of bromine, the rate would double. It wouldn't quadruple because it's first order, not second order. If we triple the concentration of bromine, since it's first order with respect to bromine, the rate would triple. So the rate will change differently when we change the concentration of bromine as compared to HCOOH because they're different orders. Okay, so let's look at another sample rate law and try to understand what it tells us. For this rate law, we're writing a rate law for the reaction shown here, where we have NO2 plus carbon monoxide yields 1 mole of nitrogen monoxide and 1 mole of carbon dioxide. The rate law for this reaction is given as the rate is equal to our rate constant K times the concentration of our first reactant to the second power times the concentration of our second reactant times 0 power. So we would say that this reaction is second order with respect to nitrogen dioxide and 0 order with respect to carbon monoxide. Overall, the reaction is going to be second order because 2 plus 0 gives us 2, of course. Now, one thing, if you have a reactant that is 0 order, as we'll see, the concentration is independent of that reactant. And so we often will write the rate law without showing this. So we could write the rate law either way. So be familiar with both of these. So as we said, the reaction is second order with respect to NO2. And what that tells us is how the rate of the reaction depends on this concentration. And since it's second order, if we double the concentration of NO2, since it's second order, the rate would increase by a factor of 4. If we should triple the concentration of NO2, because it's second order, the rate of this reaction would increase by a factor of 9. With carbon monoxide, since it's 0 order, if we double the concentration of carbon monoxide while holding the other reactant concentration constant. If we double this concentration, since it's zero order, anything to the zero order gives us 1. So if we double the concentration, the rate will remain constant. If we triple the concentration of carbon monoxide, since it's zero order, the rate would remain constant again. So we can change the concentration of carbon monoxide any way we like, but the rate will not be affected. So we could say that the rate is independent of carbon monoxide concentration, and therefore that's why we can not write it in our overall final rate law. So we talked about the orders of a reaction and said they're not related to the stoichiometry. We have to determine them experimentally. So how would you determine these orders? Well, we would use something called the method of initial rates. A couple of things about the reactions. Reactions are reversible. So as the forward reaction begins to proceed, eventually the products begin to accumulate. As the products begin to accumulate, the products can react to reform the reactant. So the reaction, we say, is reversible. And almost all reactions are reversible to some extent. And so as the reverse reaction begins to occur, the forward reaction begins to slow down some. So it's best to measure the rate of a reaction very early on before there's any buildup of products. So that's why we use the method of initial rates. We measure the rate of a reaction very early in that reaction before we have any accumulation of products. So here is a series of experiments that were performed, and we're going to use these to determine the orders of a reaction. So here's our chemical reaction. 2 nitrogen monoxides plus oxygen, 1 mole of oxygen, produces 2 moles of nitrogen dioxide. The general rate law for this reaction would be the rate is equal to our rate constant K times the concentration of one reactant raised to some order times the concentration of the other reactant raised to some order. So what we have here is some experimental data. We conducted 1, 2, 3, 4 experiments. So we performed this particular reaction 4 times, and we changed the initial concentrations of our NO or our O2. And then we measured the rate early on, so our initial rate, for each of these reactions. So this is the experimental data that we produced when we performed this reaction 4 times at different concentrations. We're going to use this data to determine what these orders, here M and N, what these are. So the first thing you want to do is pick one of your reactants and determine the order for that reactant. So let's determine the order for NO first. To do that, we want to look at our experimental data down here, and we want to choose 2 experiments. In these 2 experiments, we want to hold the concentration of our other reactant, O2, we want to hold it constant, and we want to change the concentration of NO. So if we look at experiment 1 and experiment 2, the concentration of O2 remains constant, but the concentration of NO is doubled from 0.015 to 0.030. And then we look at what happens to the rate. So when I double the concentration of NO, holding the concentration of O2 constant, so I've got a little 2 here, I can see that the rate, if I compare these 2 rates, the rate increases by a factor of 4. So in order to, if I double the concentration, in order to get a rate increase of 4, my exponent here must be a 2. So I would say that this is second order with respect to NO. So now I want to determine the order of the reaction for O2. So I do a very similar process. I look at my data and I pick any two reactions where the concentration of NO is held constant and the concentration of O2 is changed. So I'm going to pick experiment 1 and experiment 3 because the concentration of NO is constant in those two, and the concentration of O2, in this case, it doubles. So now I compare the rate change from experiment 1 to experiment 3, and I can see that the rate doubles. So if I double the concentration of O2, the rate doubles. So the exponent required to give me that would be a 1. So that would mean that my order with respect to O2 would be first order. So I could now write my rate law. Rate is equal to K, my rate constant, times the concentration of NO squared, or second order, times the concentration of O2 to the first power, or first order. And the overall reaction order would be 2 plus 1, or of course 3. The last thing we need to be able to do is determine the value of our rate constant K. So to do this, it's not terribly difficult. We just select any of these 4 experiments. For our purposes, let's select the first experiment. So we're going to look at we're going to use this as our concentration of nitrogen monoxide. We're going to use this as our concentration of oxygen, and we're going to use this as our rate. Okay, so we select experiment 1, and we're going to plug in this as our concentration for NO. We're going to plug in 0.015 as our concentration for O2, and then our rate, we're going to plug in 0.048. And the units, of course, of our concentrations are molarities, and the units for our rate are molarities per second. Okay, so we're going to select that data. We're going to plug in those values. Here you can see I've plugged in the rate, I've plugged in the concentrations, and I'm going to solve for K. Now don't forget your exponents. Since it's second order with respect to NO, we have to square this value, and since it's first order with respect to O2, we can leave this as is. So here you can see I've plugged in my data, I've solved for K, and I get a K value of 1.4 times 10 to the 4th, and the units for this particular K value are molarities to the -2, seconds to the -1. Always watch your units. So the units for K depend on the order of the overall reaction. Here you can see some of the units, but again, it's always important to plug those in as you're solving it so that you can mathematically check your answer. Okay, so let's take a look at a sample problem involving rate laws. In this problem, you have a chemical reaction, CH3CO2 CH3, and that reacts with the hydroxide ion to form our two products. In this problem, you're given a set of experimental data where you have changed the concentration of either reactant, and you've measured the initial rate of the reaction. So it says use the method of initial rates to determine the rate law and the value of K for this reaction. So take a minute or a few minutes and pause the video, attempt to solve this problem, determine the rate law and the value of K, and then finish watching the video and see how you did. So the first thing I would do is write my general rate law. The rate law is always going to be written as rate is equal to some rate constant K times the concentration of your first reactant raised to some power, some order, times the concentration of your second reactant raised to some order. So the first thing we need to do is determine the order of the reaction with respect to one of our reactants. So let's determine the order of the reaction with respect to our first reactant, CH3CO2 CH3. So we're going to need to select two reactions where we hold the concentration of our other reactant, OH minus constant. And you can see we do that in reaction 2 and 3. experiment 2 and 3, and we change the concentration of the reactant we're interested in. So here you can see the concentration of CH3CO2CH3 is doubled. So when the concentration of our reactant is doubled, the rate of this reaction doubles as well. If we compare these rates, we'll see that they double. So we can set up a little formula here. If we have a 2 here because we're doubling the concentration of CH3CO2. This is the order. And when we double that concentration, we saw that the rate doubles. So we put a 2 here. So X must be first order with respect to CH3CO2 CH3. So we know that the order of our first reactant. So we next want to determine the order of our other reactant. We do that the same way. Let's select two reactions, reaction 1 and 2. We select these because we're holding the concentration of our first reactant constant, and we're changing, in this case, doubling the concentration of hydroxide. When we double the concentration of hydroxide, if we compare these rates, we see that the rate doubles as well. So we could set up our formula, and our 2 here is because we double the concentration, and when we double that concentration, the rate doubled. So we put a 2 here. So the order must be a 1. So this is first order with respect to OH minus. So now we know the orders of both reactants. First order with respect to CH3CO2 CH3, first order with respect to hydroxide. The last thing we need to do is determine our value for K. To do that, we want to select any of the 3 experiments and plug in the concentrations for that experiment and the rate for that experiment into our rate law. So I'm going to select the first experiment, and I'm going to plug in the concentration, this concentration into my rate law. I'm going to plug in this concentration into my rate law as the concentration of OH minus, and I'm going to plug in the rate here as the rate for that reaction. When I do that, be sure to include your units. Okay. So that's what I've done here. You can see that I've plugged in the rate from experiment 1 along with the units is equal to K times the concentration of CH3CO2CH3 here, and don't forget your exponents, and the concentration of hydroxide from experiment 1 here along with the order here. Solving for K, I get a K value equal to 0.14, and the units, because this is a second order reaction, the units are molarities to the -1, seconds to the -1. So that gives me my complete and final rate law. Rate is equal to the K value times the concentration of the first reactant, first order, second reactant, first order. And so having this rate law, now anytime I perform this reaction at a given temperature, I can plug in the initial concentrations and I can determine what the rate will be for that reaction. And I can do that without having to go through all the labor of having to experimentally perform the reaction. So I can determine the rate for this reaction, and that's the useful application for the rate law.